Now let's talk about the second intermolecular force on the menu here, and that is the dipole-dipole interaction. So what the heck is that? Okay, so here in this scenario, I'm going to show you two different types of substances. Over here on the left, I have a collection of fluorine, molecular fluorine molecules. This is one of the homonuclear diatomic molecules, whereas on the right I have a different substance. It's also a diatomic molecule, but this is bromine monofluoride. So the way you can kind of think about this is, whereas these are both fluorines, what I've done to go from here to here is I've simply substituted a bromine for one of the fluorines. Okay, and that has big consequences in terms of the charge. The nature of the charge distribution around this molecule. With molecular fluorine, because it's a homonuclear diatomic, there's obviously no difference in the electronegativities between the two atoms that are engaged in bonding. And so the bonding electrons are going to be shared absolutely evenly, and so there's no net charge around the whole molecule. Now over here, because bromine is significantly less electronegative than fluorine, fluorine is going to be definitely dominating the tug of war of electrons. So fluorine is going to have a significant negative partial charge. Bromine will have a significant positive partial charge. If you look at your electronegativity table, you'll notice that while fluorine is 4.0, bromine is only 2.8, so no contest there. All right, so as a result, you've got these kind of like with a magnet, right? With a magnet, you've got a north and a south pole, so we call those magnetic poles. Well, here, because it's about because the positive and the negative ends are the result of electron an imbalance in the sharing of electrons, it's like an electric dipole, all right, with a positive and a negative pole. Okay, and here, let me just, at least for the top three molecules, let me superimpose the molecular dipoles for these guys. All right, so they're pointing toward the fluorine in each case. And so kind of like, oh, I beg your pardon, kind of like when you have a collection of bar magnets, that they're going to want to sort of snap together, right? North is attracted to south, and there'll be a force of attraction, and you actually have to pull a little bit to get those magnets apart. Well, likewise, if you have a collection of molecules with dipoles, if you kind of, don't jiggle them around too much, they're going to want to snap together, positive to negative, and it's going to take some force to pull them apart. And so as a result, you get these so-called dipole-dipole interactions. And that's all it is. That's what the dipole-dipole interaction is all about. So whenever you have a compound that does have a molecular dipole, then they're going to manifest a dipole-dipole interaction when you get them together. So these molecules are going to be harder to pull apart than these molecules. And so here's one way here's one consequence. So let's say we're going to try to heat these guys up, molecular fluorine, and see if we can get them to vaporize, go to the gas phase. So we apply a little bit of a heat, and before you know it, off they go. They start to vaporize, and now they're a gas. That was, pretty easy. Now over here, if I apply the same amount of heat, now I'm trying to show it a little bit more realistically. So what I didn't show over here was before they start to come apart, they're going to start, moving and vibrating, rotating a little bit more vigorously. But they're not going to vaporize at the same temperature that it required for the molecular fluorine. Here with these guys, because they're sticking together more strongly, we're going to have to supply more heat energy and get them going even faster. All right, and only then will you be able to, persuade them to separate from each other. You know, they're much more reluctant to move away from each other than molecular fluorines are. Okay, so and here, you know, look at the difference in the boiling points. I mean, bromine monofluoride will boil at 20 degrees Celsius, which is about room temperature, whereas molecular fluorine, you know, this thing's going to vaporize and go to the gas phase all the way down at 184 degrees below 0 Celsius. So there is roughly a 200 degree difference in their boiling points, and it is largely due to this dipole-dipole interaction. Okay, just to kind of summarize here, so what you need to know is that the boiling point of a substance is a really good indicator of the strength of the intermolecular forces between molecules. All right, so the stronger the intermolecular attraction between molecules, in general, the higher the boiling point is going to be. Okay, and this is just a final summary of this concept. Okay, so as the intermolecular attraction gets stronger, it's going to take more kinetic energy to pull them apart, which means higher temperatures required, and that's what leads to the higher boiling points. Okay, so I tried to give you a little logic chain to you know, kind of solidify this point. Now, before we go, let's take an example and let's see if we can figure this out. So we've got two compounds, two containers: hydrogen monofluoride, boron trifluoride. Okay, we have, as I said, we have containers of each. Let's say they're both in the gas phase right now. I'm sorry. Let me back up. Let me rephrase that. Let's just go with what I have here in text. Which compound do you think has the higher boiling point? Okay, so let me try to step you through a good way to approach this kind of a problem. So step one, you've got to know what the structure, the three-dimensional structure of these guys looks like. So first, let's draw our Lewis structures for each compound. Then we can determine the 3D structure because of your, you know all about geometries now. Then, based on the electronegativity differences, we can assign bond dipoles, and between the bond dipoles and seeing the 3D structure, we can determine whether they have molecular dipoles. And if one does and one doesn't, then that will give us a very good clue as to which one has the higher boiling point. Okay, so this is kind of a, this is one strategy we can follow. All right, so let me see if I can get my pen to draw here. Okay, so hydrogen fluoride is the Lewis structure is pretty straightforward, right? And fluorine has 3 lone pairs. Over here, boron. Now boron only has 3 valence electrons, so it's gonna bond to each of those 3 fluorines with no lone pairs at all, right? Here's the fluorines. They both have 3 pair, or they all have 3 pair, I should say. Okay, so now let's go back to hydrogen fluoride. Well, this one is just dirt simple, right? It's only got 2 atoms, so it's linear, right? And the dipole, does it have a dipole? Yeah, absolutely. Fluorine 4.0, hydrogen only 2.1. So there's a big honkin' dipole that points just like that. Now, what about boron trifluoride? Well, if you look at the central atom, you see that it has 3 electron domains, no non-bonding domains. So whenever an atom has 3 electron domains in total, let's see if you can draw the most stable 3-dimensional structure. Okay, so according to VSEPR theory, hopefully you came up with something like this, which we call trigonal planar. The bond angles are all 120 degrees, right? And now let's look at the bond dipoles. Do these bonds have dipole moments? Absolutely. Fluorine is kind of the gorilla of the electronegativity world, so nothing is more electronegative than boron. I'm sorry, than fluorine. It's getting close to lunchtime. Blood sugar's going down. So all three bond dipoles are pointing toward fluorine, but because they have this threefold symmetry, right? They're all the bond angles are 120 degrees. These three bond dipoles are going to cancel each other out. So there is no dipole moment at all. So based just on the simply on comparing, dipole-dipole interactions, we would say that hydrogen fluoride is going to have a higher boiling point than boron trifluoride. Why? Because boron trifluoride has no dipole, therefore it's probably not going to, stick together as strongly as hydrogen fluoride, which does. So these guys are going to be sticking to each other like little bar magnets, and if it's harder to get them apart than boron trifluoride, it's probably going to have a higher boiling point. So let's take a look. And indeed, we see that there's over 100 degrees difference in their boiling points. Hydrogen fluoride boils, again, right around room temperature. Boron trifluoride will boil all the way down at minus 100 degrees Celsius. Okay, so I hope that helps. I hope those kind of problems help kind of solidify things. So I'll see you at the next video for London dispersion.